Okay, so I know I was planning to do this lecture actually after I get some feedback from the arc length section, but then I felt like maybe I should just make this lecture because there's some simplicity to it, and it kind of boils down to some formula again, a simple formula, but there are different cases, so we have to consider that. But I think it's something that if I go through the lecture, many of you can do the homework for this section, and then we can maybe make another video for you guys if you have like some other questions from the two section. Please post them for me, and I can do some for you. Now, the idea here is, and again, when I say surface areas, a lot of students think about, okay, well, surface area of other many shapes. Many shapes have surface areas, and are we kind of trying to find surface area of all those shapes? Formula for those. There's this topic gets revisited in chapter 15 and 16 of the book in two quarters when you guys are in Math 1D, where we have to calculate the surface area. In fact, we integrate over the surface. So if something to give you guys motivated for that time, if you go that far up in the calculus ladder, but so there's a general concept of surface areas. Even especially there, we're actually going to talk about parametrizing surfaces and calculate their area. But here we're talking about the specific type of surface. We're talking about the surface that's created by rotating a function. So you have a function, you rotate it like we did with the chapter 6, you rotate it, you get some solid of revolution, and then you're calculating the surface of that solid. So that's what we're talking about. We're not talking about all or any surface, it's just a specific type of surface. Again, it's a function, it could be a function of x, it could be a function of y, and the rotation could be about the x-axis or it could be about the y-axis, and it could be about other axes, other lines as well. But the focus in this section is, and I see some value to just focusing on that type, but the focus in this section is just to consider functions of x or y, and then rotation either about the x-axis or about the y-axis. So those are the only types that we're focusing on, and I break it down into different cases, and I help you guys hopefully to recognize when to use what formula. So in a very simple form, if I think about a function that looks like this, and I rotate it about the x-axis, for example, what I end up with is what we call a frustum of a cone. And what the frustum is, if you consider a cone, frustum is actually just a part of that cone. And you're trying to calculate the surface of that frustum, surface area. Now, to begin with, we have a formula for surface area of a cone as a whole, without just considering part of it, surface area of a cone as a whole. And that surface area, if you think about the cone as a sector of a circle where you glue this part to this part, and then you form your cone, then you can calculate the surface area of the cone by calculating the area of this piece. Now, if the diagonal length of the cone is L and the radius of the base is R, obviously this portion matches the circumference of the circle. So this is going to be 2 pi R. This is L. So this is angle theta. Area, and from geometry, area would be 1/2 L squared times theta. And theta is 2 pi R over L, because you divide the arc length by radius, you get angle. If you remember in a previous lecture, I told you guys that arc length is radius times angle. So if I want angle, I divide arc length by radius and I get the angle. So that's what the theta is. One of the L's cancel out and twos cancel out. We get pi r L as your formula. That's for the full cone, calculating the surface area of the full cone. That's something you probably borrow from your geometry or trig class, maybe. I mean, we were talking about it. It's a very simple idea to talk about right after when we talk about this arc length and the connection of arc length and the angle and the radius. So it's a, as I said, it's not something you should worry too much about it. I'm not going to ask you guys to derive this formula, but I would like you to see it and know how to do it, just in case on the test you forget. You're like, well, not this formula actually, but in general, if you're trying to come up with this or use this formula, and on the test you kind of forget, you're like, what was that formula? You can just go ahead and derive it quickly. At least know what the variables are that you're going to use or what the parameters are. But our story is to calculate the area of surface area of that frustum. And if I call this radius L1, I mean this diagonal length L1, and of course this is L, that's our focus. Then basically what I want to do is I want to calculate the surface area of the whole cone minus the surface area of the top part of the cone gives me the surface area of the shaded region. I need to also name my radii. Let's call this R1 and let's call this R2, just for simplicity. Okay. So surface area of the whole thing would be, so shaded region would be surface area of the whole thing, which is pi R2 L1 plus L. And the surface area of the top part without the shaded part would be pi R1 L1 actually, sorry. So if I just multiply and factor, I have pi R2 L1 and pi R1 L1. So it's going to be pi L1 R2 minus R1 plus pi R2L. Now, yeah. Again, my whole goal is to get some formula for this frustum, and then I'm going to explain what's the connection of that frustum to the area to the whole thing. But let's just go through this last few steps to come up with that formula. Now, if I look at this portion, I actually see two similar triangles. One triangle is here with the right angle, one triangle that's here with the right angle, right? Which gives me Euclid's formula for similar triangles, which means L1 over R1 is equal to L1 plus L over R2. So L1 over R1, L1 plus L over R2. Oh, sorry. Let's see this. Sorry, one more time. L1 over R1, L1 plus L over R2. L1 over R1, L1 plus L over R2. If I look at these two similar triangles, let's flip up the other side. Okay. So that gives me a nice formula that says L1 R2 is L1 plus L R1. Now I want to create that R2 R1 situation. L1 R2 minus R1, if I take this combination to the left, is equal to L R1. So this is going to be LR1, this is LR2. So the area of the shaded region is going to be pi LR1 plus LR2. Multiply and divide by 2 is going to be 2 pi L R1 plus R2 divided by 2. It's average of R1 and R2. Let's just call it R star. Okay, and again, you'll see that in calculation, that's the same thing we do going to do the parameterization, partitioning, taking the limit as partitioning. Gets bigger and bigger, or the width gets smaller and smaller. Okay, so why is this important? Why is it important to calculate the area of a frustum? Because what is happening really is that when I have a solid of rotation and I want to calculate the surface area of that, that solid, as I rotated it, each portion looks like a frustum. Where if this is xi and this is xi plus 1, the radius of this would be f of xi, and the radius of this would be f of xi plus 1. L in this picture, the L part is going to be the arc length. Arc length plays a role, the same formula that we used before in the last lecture. So I know my L1, which gives me my, my R1 and R2, the two radii. And I'm going to use one of them, or the average of them in a way, that would be my Ri star. And I have 2 pi, that's average of the two radii, times L, which is going to be the arc length. So in that language, the area of this part of the surface is going to be 2 pi yi plus yi plus 1 over 2, and then the distance of the two, which is going to be some sort of a straight line from those two. So if I give them point names between these two, and I call one of them as pi, one of them as pi plus 1, is going to be the distance of pi plus 1. This, of course, is the arc length formula. It's going to be square root of 1 plus f prime of xi star, whatever that, square over delta x. Putting all these things together, you're going to get the surface area is approximately sum I equal to, with my writing, 0 to n minus 1, 2 pi f of xi plus f of xi plus 1 over 2. Times square root of 1 plus f prime of xi star delta x. This one, because it's the average of the two, we can just replace it with fi. Now you have to be careful here, but as the limit goes on, let's call it f of xi. Star maybe. Times square root of 1 plus f prime of xi star. They don't have to be the same thing. And finally, SA, the actual surface area after taking the limit, will be the integral from some a to b of 2 pi fx square root of 1 plus f prime of x squared dx. This plays the role of the radius. This is the plays the role of the L part, the L part. Again, sorry, the L part. And of course, the rest of the formula is supported by my derivation. You need not know the derivation, but I hope you know enough of it to be able to derive it in case you didn't write the formula on your note sheet and you forget it on the test, or maybe it's quarters after now and you really need it, and then you just quickly derive it so you have it in front of you. And the derivation relaxes you, I think. It's very relaxing derivation. Okay, it's simple in idea, but so let me leave this here. I want to go to a different page, but let me leave this here for now. Let's go to a different page together. What really happens is I can just rewrite this as ds, and fx is y, and I can bring out the 2 pi out. So that's really your surface area in this notation. Now, this is what happens when you rotate it about the x-axis. But if you were to rotate it about the y-axis, then your radius would not be y, your radius would be x, because you have the radius from the axis of rotation would be x, not y. So we have a following breakdown. And again, just remember this. I think that will get you through the problems and it helps you understand it. But you may want to look at this a couple of times when you're doing problems just to make sure you're choosing the right form. So one breakdown is if I rotate about the x-axis versus if I rotate about the y-axis. If I rotate about the x-axis, my integral is going to be 2 pi integral, my radius would be y ds. And if I rotate about the y-axis, it's going to be 2 pi integral x ds. So the choice of x or y is not dependent on what's a function of what. It's just dependent on, which is going to be the next level. It's dependent on where you rotate, x-axis or y-axis. But then you have 2 cases for each. Either you have y to be a function of x, or you have x to be a function of y. What that will do is that will determine whether or not you should use, which form of ds you should use. So if y is a function of x, then you have the most generic form of this. Y is a function of x, and your arc length formula, the ds part, would just be 1 plus f prime of x squared dx. But if x is a function of y, then you just leave it as y. Your integral is going to be y dy, and your arc length would be f prime of y squared dy. So since you're going to have a dy, you leave this as y and don't convert it to fx. If this was a dx, you leave it as fx. And again, whether it's dx or dy depends on is y is a function of x or is x a function of y. That's what determines what form of ds you use. The form of ds depends on is y a function of x or is x a function of y. Same thing here. If you're rotating about the y-axis now, the radius would be, if I'm rotating about the y-axis, the radius would be x. And then the ds part, if y is a function of x, would be square root of 1 plus f prime of x squared dx. If x is a function of y, it's going to be 1 plus f prime of y squared dy. But that will mean that I have to replace x, because everything is in terms of y, you have to replace x with f of y. And that's how the breakdown works. So depending on whether or not you rotate about x or y axis, you use either y ds or x ds. And depending on whether y is a function of x or x is a function of y, then you use a different form of your ds. There's a lot of like symmetries going on here, but that's a big part. That's it. If you can separate or you can distinguish between these forms for yourself during the test or as you're doing the homework, then you're all set. Just remember when to use which one, and it's really breakdown with this tree of conditions. Let's do an example together. Let's do number 7, I guess. 7 is again we're in 8.2 right now. 7 is y equal to x cubed. X is between 0 and 2. And it's rotated about the x-axis. Okay, so rotated about the x-axis, I'm going to have surface area to be 2 pi y ds because it's about the x-axis. And y is a function of x, so we're going to actually apply the top form. So it's going to be 2 pi, x goes from 0 to 2, f of x, which is your y, is x cubed, 1 plus 3x squared dx. Just took the derivative and squared it. So it's going to be 2 pi 0 to 2x cubed, 1 plus 9x to the 4 dx. And let 1 plus 9x to the 4 to be 36x cubed. Sorry. I don't know what I wrote there. It's u is equal to, and then my apologies, and then du is equal to 36x cubed dx. If I just follow through with that, I get x cubed dx would be 1 over 36 du, and let's just go with that. So I have 2 pi 1 over 36 du, and that's square root of u. And let's just go ahead and plug in. If it's u, x is 0, u is 1. If x is 2, you get 16 times 9 plus 1. So you plug in both bounds. So 9 times 16, 144 plus 1 is 145. So I get pi over 18 u to the 1/2 to the answer there would be 2/3 u to the 3/2 from 1 to 145. So pi over 27, 145 to the 3/2 power minus 1 to the 3/2 power. And you can let the calculator help you with that. Let's do number 13. Again, still in 8.2, number 13. Now, x is equal to a function of y. Still rotated about the x-axis, but x is a function of y. So about the y x-axis, we use this form, but x is a function of y. This is a formula I want to write. So it's going to be 2 pi integral y square root of 1 plus f prime of y squared dy. Not too bad. 2 pi y goes from 1 to 2. Now derivative of this is 1/3 times 3/2 y squared plus 2 to the 1/2 power times 2y. So 3, 3, 2, 2 cancel out. I get y squared plus 1 to the 1/2. Okay, so it's going to be y squared plus 1 to the 1/2 squared, that's your f prime of y squared, plus 1. It's going to be 2 pi y squared plus 1 plus 1. Again, you choose the form based on 1, what are you rotating about? And then 2, what will your ds form be? Okay. Yeah, and then you can integrate this part. Now, yeah, that's okay. Now, if you do number 15, that's rotating about the y-axis. And it's y equal to 1/3 x to the 3/2. X is between 0 and 12. Since the rotation is about the y-axis, is 2 pi x ds. And since y is expressed as a function of x, it will be this one. So surface area is going to be 2 pi x from 0 to 12, square root of 1 plus derivative of this. 3/2 times 1 is 1/3 is 1/2 x to the 1/2. So 1 plus 1/2 x to the 1/2 square quantity dx. One half x to the 1/2 square is 1/4 x plus 1. A use substitution here can help you solve this. And I think for my final example on this one, we'll do number 17. Yeah. Now for 17, actually, let me do 18 because 18 is a trick that I told you guys about in last lecture. So let's just remind you guys of it. Yeah, 18 looks nice. Y equal to 1/4 x squared minus 1/2 ln of x. We saw this in last section. Then again, because it's rotated by the y-axis, is going to be x and then square root of 1 plus. Derivative of this is 1/2 x minus 1/2x. I think now you guys recognize what I'm talking about. If you watched the last lecture, last video. Again, rotation tells me it's x. And then because y is a function of x, that means you're going to put dx here. And then this part, the ds part has dx in it. If I expand this, then as you would expect, since you saw last lecture, is 1/4 x squared minus 1/2 x plus 1/4 x squared. So not 1/2 x, just 1/2. And then if I combine this and this, I get surface area is integral from 1 to 2 of x square root of 1/2 x plus 1 x squared. And then if I fall it out, because the square and square cancel, if I distribute it, then I get 1/2 x squared plus 1/2 dx, and which is an easy calculation. Okay. Surface area is not too bad. The derivation is one thing. Whether or not you're interested in the derivation, know how the derivation works, have it in your mind. And then deciding which form to use based on your rotation and based on either y is a function of x or x is a function of y. But I hope this table breakdown helps you, because then you can always decide based on whether or not the rotation is about x or y axis and whether or not the function y is a function of x or x is a function of y. And I hope that helps. So these two lectures that I am posting should help you get through the homework. And then if you have still problems with some of the homework problems, I can make an additional lecture video just on problem solving content, which I hope that will be a little bit more helpful and beneficial to you guys. Well, thank you.